This is the ANOVA topic 13, recording 2. And we just finished the example of fiction and film and social cognition. And we used ANOVA to test the hypotheses because there were 3 groups. ANOVA is just analysis of variance. And we'll be talking about 2 types. One-way ANOVA, where you have one independent variable, also called a factor. And we'll talk about factorial ANOVA in the next topic, where you have 2 or more factors. The important thing about ANOVA is you can compare means for more than 2 groups. For 2 groups, you can use a t-test, as we've learned, but you can also use an ANOVA. And this would be useful if you continue to study more statistics. You'll learn that you can use an ANOVA, and that allows you to make it an ANCOVA and include a covariate and control for other variables. ANOVA can control for multiple tests, and it can control for other variables, as I said, used as covariates. So an ANOVA tests the effect of an independent variable on a dependent variable, just as an independent samples t-test would, right? Or paired samples for that matter, but we're not going to talk about that type of ANOVA. As I said, a one-way ANOVA has one independent variable, and a two-way has 2 independent variables or 2 factors, also called a factorial ANOVA. Independent variable is referred to as a factor. If independent samples, that means that people in the groups, in the different groups of the independent variable are the different people. It's a between subjects or between groups factor. And we talk about it as a between subjects or between groups ANOVA. This is the same as an independent samples t-test. You cannot have the same people in the different groups or people who could be expected to respond in the same fashion. You can also use related samples in ANOVA, and it's called, in that case, repeated measures ANOVA or within subjects ANOVA. You don't need to worry about this one for this course. So factors. Factor just means an independent variable. Okay, it's just anything where you have groups of people, right? So conditions of the independent variable are called levels, treatments, or groups. So in our example, we had the independent variable with our factor was type of television, and we had 3 groups: drama, documentary, and control. We could also call those 3 levels. K is used to indicate the number of levels. So in our example, K was equal to 3. Another example would be depression. Say you randomly assigned participants that came to a clinic to either receive a medication, to cognitive behavioral therapy, or to a waitlist control group. Okay, that will also be 3 groups. So K equals 3. The dependent variable is also called the outcome variable or measured variable. Thinking of it as a measured variable is good because you can think, we'll measure depression after people are randomly assigned to groups. In our example, we measured social cognition after having people randomly assigned to view either documentary, drama, or nothing, right? Your dependent variable, just like with t-test, must be a continuous interval ratio variable, and it should be normally distributed. This is the first assumption for an ANOVA, that the dependent variable is normally distributed, which means it must be interval ratio. The second assumption, as we've already mentioned, is that there's one independent variable for a one-way ANOVA, and all the conditions or levels of the independent variable contain different people or independent samples. Finally, the third assumption, as in our 2-group t-test, right, is homogeneity of variance. The variance of the populations of the different groups are similar. So our hypotheses are really simple. The experimental or alternative hypothesis is that the means will be different between one or more of the levels of the independent variable. In other words, not all means are equal. So mu1 is not equal to mu2, not equal to mu3, and so on, up to however many groups there are. That K just means however many. So if you have 3 groups, your alternative hypothesis is just U1 not equal to mu2 not equal to mu3. Okay, 3 groups. The null is that there'll be no difference between any of these groups. Okay, so if you have 3 groups, the null is just mean 1 equal mean or mu2 equal mu3. That's for 3 groups, right? If it were 4 groups, we would just add another one. This is supposed to be a 3 here, by the way, okay? If there were 4 groups, we'd just add another one, not equal to mu4 equal mu4. You should never have a K appear here. I know there's certain confusion with that. Okay. So we use the F statistic to test hypotheses in an ANOVA. This is your test statistic. If your F observed or obtained is significant, that means less than your alpha level, then 2 or more of the means are significantly different. This initial test is called an omnibus test. All it is, your F is telling you, is there a difference between 2 or more means? It does not tell you which specific means are different. You have to use post hoc comparisons to figure out which means are significantly different from each other. Post hoc comparisons just refer to tests for the differences between specific levels of the independent variables. This is just a series of t-tests. The p-values for these t-tests are adjusted to compensate for multiple comparisons, or they can be if you want, right? So why wouldn't we just do 3 independent sample t-tests if we have 3 groups? The reason we do this is alpha inflation, or experiment-wise or family-wise error rate. This just means that the probability of making a type 1 error is greater when you're making many, many tests, right? The experiment-wise error rate just refers to the probability of making a type 1 error across all the tests in an experiment. So if you have 3 groups, this will be 3 t-tests. F is 1 test. It tells you if there's a difference with a single test. Okay, remember what a type 1 error is, right? That's when you reject a null hypothesis that is actually true. And if there's only 1 test, your type 1 error, the probability of committing this type 1 error is just equal to alpha, which in general is 0.05. Okay? So that refers, your alpha level is the probability of rejecting a true null hypothesis in 1 test. But the more tests you have, the higher that alpha, real alpha is. This is called alpha inflation. ANOVA's F test controls out alpha inflation by using 1 test, 1 statistical test to detect differences between any of several mean comparisons, right? So let's think through this a little bit. F is your test statistic, and the critical value, that is the one that corresponds to the level, the p-value, which would be less than your alpha, depends on your sample size, which is degrees of freedom within, and the levels of your independent variable. So this corresponds to degrees of freedom between. Your effect size for the model is eta squared. So effect size just tells you how big is the difference, how much, in this case, how much of the variance is explained by the independent variable as a whole, right? Which is the same as your R squared for regression. For pairwise comparison, so if we have a significant F test, then we look at pairwise comparisons to figure out which 2 differ or more differ significantly. We use Cohen's d for those. That just tells you what is the magnitude of the difference between these 2 individual means, right? So proportion of variance explained, remember regression? That was just the sums of squared regression divided by sums of squared total. Eta squared is the exact same thing. Sums of squared between divided by sums of squared total. Sums of squared between is very similar to sums of squared regression. And we'll walk through all that, okay? So regression, remember we had sums of squares total was equal to the sums of squared regression plus sums of squared error or residual. For ANOVA, we calculate our F value by dividing our mean squares between groups by our mean squares within groups. And what does this even mean? Okay. Mean squares between groups. This is mean squares between groups, right? You just divide sums of squares between groups by the degrees of freedom between groups. Now your sums of square between groups, let's break this down. Right here, this is the mean for the group. J just refers to the group. So this is the mean of the group minus the grand mean. Okay, this is T or total, the total mean. This is just adding up the scores from every single participant in the experiment and dividing by N. This one, the mean for the group, you just add up the scores of everybody in the group and divide by the number of people in the group. So you can see that the bigger the difference between the group and the grand mean, the bigger your sums of square between group is going to be. Now, this is important. Your degrees of freedom between group is K minus 1. K, as you recall, is the number of groups. In our example, it was 3 minus 1, which was 2, right? So again, this sums of square between group, you square the value you get. So you know it's always going to be a positive number. So you square the difference between the group and the grand mean, and then you add them up. Right? In our example, there's going to be exactly 3 deviations of the group from the grand mean squared. Now, mean squares within, this is the bad stuff. This is the variability within groups. And like I said, the more variability you have within a group, the less power you have, right? So let's think about this. This is sums of squared within groups divided by degrees of freedom within groups. Here's your sums of squares within group. This is just the variability within the group, how much each individual in the group, that's X, that's an individual score, differs from the mean of the group. So this is the deviation of the individual from the mean of the group squared and summed up. Again, this is going to be a positive number, right? And this is going to be however many calculations as are individuals in the group, right? This is sums of squared error because ideally, if you were performing some kind of manipulation, you want the scores of everybody in each group to be very similar. In our example of fiction and television, we want all the eyes test scores for people who watch drama to be very high and all the eyes test scores for the control group to be very low. If we have some people with high scores in the control group, it's going to make the mean higher than we want, right? And closer to the mean of the experimental group, right? Degrees of freedom within group is just N, so the total number of people in the experiment, minus K, or the number of groups, okay? This is everybody in the experiment. This is number of groups or levels of the independent variable, all right? And this right here is just variance, right? So mean squares. Treatment variance is also another way of talking about the mean squares between groups, okay? This is very similar to sums of squares regression, except for mean squares is actually the sums of squares between groups divided by the degrees of freedom of between groups. Error variance, mean squares within groups, right? And this is just the sums of squares within group divided by the degrees of freedom within group. Okay, this is parallel or similar to sums of squared error and regression. To reject a null, your mean squares between group must be greater than your mean squares within group because this is your F statistic, right? The bigger the F statistic, the more likely it is you can reject the null. So you want the difference between the groups to be big, and you want the difference within the groups to be small. The critical value of F depends on the degrees of freedom, both between groups and within groups, right? The level of alpha that you select. And it's always one-tailed because look back here, F mean squares. Mean squares is just a sums of square deviations divided by degrees of freedom. So these have to be positive values, which means that F is always going to be positive. Okay, here is an F distribution. And you can see the region of rejection is always going to be high numbers. The larger values of F, the more likely it is you can reject that null. And this will depend concretely on your sample size and the number of groups in your independent variable. It's always a one-tailed test, but we don't have to worry about hypotheses for that. Okay, so here is just a slide that summarizes everything. Here we have, let me get a pen. Our mean squares between group, this is the good stuff, is equal to the sums of squares between group divided by the degrees of freedom between group. And again, this is the variability between levels of the independent variable. And we want this to be big. If we're testing a drug, we want the difference between it and the placebo to be huge, right? And here we just have the sum of the deviation, the square deviations between the mean of the group and the grand mean, the mean of everybody. Degrees of freedom between group is number of groups minus 1. Mean squares within is just the sums of squares within group, which is the difference, the deviations between the individuals in the group and their group mean. We want this to be small, right? Ideally. So mean squares within is sums of squares within divided by degrees of freedom within, which is n minus the number of groups. Again, F, you divide your mean squares between by mean squares within. Again, eta squared is just the sums of square between groups divided by sums of square total. And this, just like your R squared, is the proportion of variance in your dependent variable explained by your independent variable, right? You also have a degrees of freedom total, which is n minus 1, just like for a lot of things, right? And the sums of squared total, which is just the squared deviations. This actually would be a y, right? Okay, so here's a table that summarizes it, right? And this is going to be similar to what our SPSS output is. I'm going to pause this, even though it'll mean us